Hello, welcome to another episode of Cabin Fever Astronomy. My name is Joe Childers, and this today is going to be the second part of our series on the sun. So last time we talked about things that you can see in the daytime sky that are caused by the sun, different kinds of things like rainbows and halos and shadows and things like that. And then we also talked about how nuclear fusion happens at the core of the sun to generate the light and heat that makes life possible here on Earth. So today we're going to be talking about the internal structure of the sun and then talking about the Solar Dynamics Observatory, which is constantly taking movies and pictures of the sun. So touring the universe is the first segment where we're going to look at the sun itself. So here's a gorgeous picture from Wikipedia. One of the Wikipedia users made this. And so we're going to be talking about each of these parts of the sun. We're going to start with the core. That is where the nuclear fusion happens. Now it's mostly hydrogen and helium, but because of the extreme pressure, because of all of the mass of the sun, it is squished down to be 13 times more dense than lead. And it's about 28 million degrees Fahrenheit. That's what's necessary for the fusion to occur. The radiative zone is the next region outside of the core. The core and the radiative zone are dense enough that they rotate pretty much like a solid object. There isn't like different parts of it orbiting or rotating at different speeds. The reason it's called the radiative zone is that the energy, the gamma rays that were formed in the core from the nuclear fusion, the leftover energy, have to bounce around inside the radiative zone for up to several 100,000 years. The reason for this is that it is dense enough that the atoms, or rather the nuclei, will absorb that energy and then spit it out again. So there's a constant cycle of absorption of a gamma ray and then emitting a gamma ray. But the emitting isn't necessarily in the outward direction. But if you look at the section that is going down into the core, you'll see that the outer surface zone, on the other hand, is where the plasma just rises and falls in groups. So these are called thermal cells, and this is exactly the same thing that's happening in a lava lamp, except it's much, much hotter. Instead of photons, light carrying the energy from one place to another, is the heat of this cell, this region or volume of plasma, and it carries the energy upwards by simply moving. And then cooler regions higher up are coming back down, and so there's a constant cycle going on. This region is not dense enough so that it rotates as one unit, but rather the change in the latitude on the sun makes it rotate faster or slower. Granules, which you can see up in the upper left there, they are visible on the surface of the sun, which we'll get to in a bit, and those are the convection cells. So it's constantly going this way and that way. And a lava lamp is pretty much a cylinder, and there's limited options for which directions the hotter globes of wax and the lower globes of wax can go. But in the sun, being a three-dimensional sphere, it's a lot more complicated. Okay, so we talked about how the radiative zone is rotating as one object, the convection zone as differing rotation speeds based on your latitude. So the tachocline, which is that's Greek for speed boundary, that is the spot where it transitions from the uniform rotation to the varied rotation. And so there's a lot of shear going on, turbulence, and it's thought that this is the source of the sun's magnetic field. We always have a plasma on the inside, and that's a charged particle, like the electrons in an electric wire. And if you wrap that wire, you can make put a nail in it to make it stronger, but you can make a magnetic field from moving electric current. And the plasma doesn't need a wire to do this, just the movement of those plasma particles around is enough to make the magnetic field. So the photosphere, that's the visible surface of the sun. So the sunspot that you see up in the upper left, that would be visible on the surface of the sun, with the perpetual caveat, don't look at the sun unless you have prepared a filter correctly. And the webpage for NASA eclipse safety can tell you that. You would need to use a telescope to see sunspots, and telescopes come with their own solar filters, except for some very rare, very large sunspots. So the surface of the sun is almost 10,000 degrees Fahrenheit, and its air density, when you take into account the number of particles, not necessarily the mass of each particle, but it is significantly less than the sea level air density on Earth. So that is where it has gotten thin enough that it becomes transparent to visible light. And so the photosphere is the outer edge of the sun that is dense enough to be opaque to visible light. And so the light that comes away from that is light based on that temperature. And that's how we can measure that temperature, by looking at the distribution of wavelengths coming away from the sun. You'll see under the word photosphere there to the left, temperature minimum. And the surface of the sun, a little bit above the surface of the sun, is the lowest temperature in the whole sun itself. The chromosphere is invisible to visible light. It's transparent, it's not dense enough, and also because it is so rarefied and so not dense, most of the radiation that comes from it is coming from what we call emission radiation instead of thermal radiation. It also increases in temperature the farther away that we get from the photosphere. The transition region is between the chromosphere and then the outer atmosphere, the corona, that we'll talk about next. So when it says they're complicated physics, that's a euphemism for I don't understand it. There's all sorts of things going on with different types of ions. The helium ion here gradually becomes fully ionized. And there's also things going on with the magnetic field, and I'm sorry, I tried to figure that out, but you can't really explain it in layman's terms until you know it yourself. So we're just going to say complicated physics. So the corona itself is very hot, like millions of degrees hot. But like how you can stick your hand in a 400-degree oven briefly without burning it, as long as you don't touch any of the metal, but you can stick your finger in boiling water, which is half the temperature, and be instantly burned badly. It isn't just the temperature, but also the density. And the corona is not very dense. So even though temperature is saying that the particles in the corona are moving quickly, there's just not enough of them to have a significant amount of heat energy compared to the photosphere and the sun proper. Magnetic features are what dominate this. We are going to see in a bit here a picture taken of the corona during a total solar eclipse, and you'll be able to see the magnetic field, kind of like you see iron filings when you put a magnet under that piece of paper that the filings are on. The flares and the prominences, and then the sunspots too, are all caused by the magnetic field. Solar wind are particles that are lost from the corona. They stream out into the entire solar system. When they interact with Earth's magnetic field, that causes the northern lights. And sometimes when a flare is aimed correctly, they will come towards the Earth, and we will get more northern lights, and they'll be visible farther south on the Earth. Unfortunately, that can also affect our electronic equipment. The solar wind also extends way out beyond the orbit of Neptune and the Kuiper belt, and it's kind of like the edge of the sun's influence in the Milky Way. There are gases and dust particles and such in interstellar space, and they have their own motions. And the heliosphere, this term here, is where the solar wind is moving with more pressure than the interstellar medium. And so as the sun moves along, it's moving towards the constellation Hercules, incidentally. There is there's a bow shock in front of it and kind of a tail behind it. It looks almost like a teardrop, where the solar wind has more influence. And the Voyager 2 spacecraft has recently passed into interstellar space, and when they meant that, they were talking about crossing the edge of the heliosphere. Here is that picture of the corona. Now, this particular picture of a total solar eclipse, I don't recall which one, was optimized to show the structure in the corona. And so you can see that the magnetic poles are towards like 11 o'clock and 5 o'clock. And then closer to the equator, it gets more complicated. It is not a nice, relatively smooth magnetic field like we have here on Earth. Here's the close-up, and you can see prominences also during a total solar eclipse because they are wider than the moon's diameter. And both the corona and the prominences are normally invisible because of the glare coming from the photosphere. And of course, there will be a total solar eclipse right here in the Miami Valley on April 8th of 2024. Now we're going to talk briefly about the Solar Dynamics Observatory. This is orbiting in interplanetary space between the Sun and the Earth. So it's not in orbit around the Earth, it's in orbit around the Sun. And it's always facing the Sun, and it has several different instruments. The four up at the top with the colored filters are used to look at the Sun excuse me, to look at the sun in different wavelengths, particular wavelengths. There are various filters that will zero in on just one color of light, which is associated with a particular ion. The one in the lower right is studying the interior of the sun. Here is the view through hydrogen alpha. That is one of the wavelengths that ionized hydrogen will emit. And this is what a backyard solar telescope or a more expensive versions of the solar filters that you can put on a telescope is viewing in. This is taken earlier this morning, so it's just a capture from the Solar Dynamics Observatory website, and you can see the prominences very well in this wavelength of light, and that's why it's popular with amateur astronomers. It also takes movies. This is zeroing in on the light that's coming from iron atoms that have had 9 electrons taken away from them. So you can see more of the motion that's not only just the variations in the magnetic field, but sometimes in these you can also see the various convection cells, because there's small ones and then there's larger ones. Both this and the previous slide are not particularly dynamic because we are at the ebb of an 11-year cycle of sun activity. And from what I can tell, it's a little bit delayed in coming back, perhaps. It isn't always exactly every 11 years. It goes from our second episode about the sun. If you have any questions for us to answer in a future video, go ahead and send those in to astronomy@boonshoffmuseum.org. Please like us and subscribe to us. We are going to continue to be posting content online as long as the shelter-in-place order and the museum being closed continues. Thank you.